Okay, so I'm going to go ahead and get started again. So we're going to finish up talking about S3 classes and methods. We'll talk about S4 classes and methods, and then we'll get into looking at some of the actual S4 classes and methods we have implemented in MS Example, our MS Example package, and then we'll see, and then we will see if we have time for some doing some hands-on exercises, trying to extend MS Example a little bit. Okay, so where we were last time, we had just created constructor functions for our cat and dog classes. So we can create a cat named Mittens, a dog named Duke, and so forth. And then we created a print method. And we defined this print method on the animal superclass. So both cats and dogs will inherit from this animal class. All this print method does, it just prints that the object is a whatever cat, dog, whatever named, whatever the name is. And all we needed to do that was just follow this S3 naming scheme of the name of the generic, in this case print, dot, and then the name of the class, in this case animal. So in this case, print was already defined as an existing S3 generic function in base R, but suppose we want to come up with a brand new S3 generic function. So in this case, we're going to create a new S3 generic function called speak. And to do that, we just create a function. All the function does is it will call this other function called useMethod. And that just has a single parameter that is the string of the name of the generic that we are creating. So we're going to create a speak generic function. Just create a function, takes an object as a parameter, and it calls useMethod speak. We'll assign that to speak. Now speak is an S3 generic function that we can define new methods on. That's all we need to do to create the generic. So now let's create some speak methods for our classes. We'll start off by just making a default method. So if we call this speak generic function on any object and it's not an object that already has its own method implemented, it will fall back to this speak.default method. So let's do something reasonable. If we call speak on any random object, it'll just make some kind of weird noises. If we call speak on an animal, it'll make weird animal noises. And then if we call speak on a cat or a dog, cats will meow and dogs will go woof. So now, let's go ahead and create instances of our cat and dog class. We'll assign these to Mittens and Duke. And type them, and they will print on our command line using the print method. Now if we do speak on Mittens, Mittens is a cat, so Mittens will meow. We'll speak on Duke. Duke is a dog, so Duke will go woof. Woof. We call speak on list. What will happen? Yeah, it'll just make some weird noises because that's the default speak method that we implemented. So in summary, for S3 class, all we really need to do is set this class attribute somehow. We created constructors for our cat and dog class that properly sets this class attribute along with whatever things we happen to need. In this case, we just have the name of the particular pet or animal. We created a print method. We created an S3 generic function like this. And we defined S3 methods for this speak generic function, a default one, an animal one, then ones for cats and dogs specifically. And we showed that's all we really needed to do to get that working. So now speak can be specialized for any class that we want. Any general questions about this S3 system? Yes?
Are there any special default, seems like a special reserved way of building these? Are there other things like default?
Not that I am aware of, but yeah, some of these things, ultimately S3 is really just this naming convention, and by convention.default is the default method that will be called if there isn't another one. Not sure if there's any other ones that behave quite like that. Gabriel's shaking his head no at me, so I guess not. Yeah, that's the only one apparently. Any other questions? So that's really all we'll talk about S3 for now. So S3 is really simple. It's relatively easy to use. That means it gets used for a lot of things in base R. A lot of CRAN packages will use S3 because it's really all that they need. Bioconductor will typically use S4 classes. S4 classes have a formal class definition like you'll usually get in other object-oriented programming languages like Java or C++. So the S4 class system adds a formal definition of the class data structure. So S4 classes have what are called slots, and these are essentially variables that belong to that particular to an object of that particular class, but they're accessed in a special way. And you access the slots via this @ operator. And S4 classes, these slots, you have control over what data type they're supposed to be. So when you first define an S4 class as a formal class, you specify what the slots are, the names of those slots, and also what data types are acceptable for those particular slots. So this is essentially the closest R gets to actual type checking. So if you want something to be, if you specify that you need a slot to be an integer and it's not an integer, it will not be a valid instance of that particular class, and you'll get an error when you try to call valid object on it. The inheritance used by S4 classes is more formally defined rather than just an attribute. So when we did inheritance with S3, all that was just additional elements in this class character vector attribute. With S4 instead, since we have formal class definitions, that means that inheritance is also formally defined. Method dispatch can happen on multiple arguments, so we can specialize a method for more than just the first argument. And we can actually check whether an object is a valid object of that particular class. So for example, checking things like checking all of the slots of the correct data type, and we can check other things like making sure the number of rows is the same for all columns, or checking that the number of columns in row data matches the number of actual rows in some assays or something like that in the case of summarized experiment. So we can think of some S4 classes that you might already know. Yes?
So what is the point in the method dispatch of multiple arguments on the first one? We also learned that ST just specializes on the first argument. So what does it actually mean?
Okay, so for example, for plot, by default plot is an S3 method. Let's see. Forget where the S4 version of plot is. So in the S3 version of plot, we can only define methods for the first argument x. So if we give plot a data frame and some other stuff, it will only care about that first argument, and that first argument is a data frame. However, with S4 methods, we can actually dispatch on multiple arguments. So plot, the generic function for plot, has two arguments, x and y. And so we can define specific methods that depend on both the class of x and the class of y. So we could have a plot method that does something differently depending on whether we give it a data frame and another data frame, or a data frame and nothing, or a data frame and a vector, or a data frame and a formula, and so on and so forth. So we can specialize on more than just the first argument of the generic function. Any other questions on this basics of S4 classes before we keep going? Right, so if you've used bioconductor before, you've probably already used some escort classes. Can anyone think of some escort classes that you might have used, or there's a few that we've already mentioned at some point? Yes.
Yes, MS Stats S4.
MS Stats, the package, I don't think it actually has any, I'm not sure if it has any S4 classes in it, but MS Stats itself is a package, and Sunghang, does it have any S4 classes in it?
No.
No. So MS Stats primarily works on existing data sets, so it doesn't really define its own classes. It just works on data that you give to it. So some packages won't create their own S4 classes. They'll just use classes that other packages have defined. Vincent named a few the other day. Anyone remember what those were? So one of the ones that he mentioned was summarized experiment. So summarized experiment, go back, is one of the, wait, actually I don't need it back, I have it here. So summarized experiment is an S4 class defined by the summarized experiment package. This is one of the core bioconductor packages now. Summarized experiment is used extensively by other bioconductor packages, mostly for genomics data. But essentially you have an assays slot. This assays slot is usually some sort of list of multiple assays. What class is this slot? This assay slot has to be an object of the class assays. You have a call data. This is a data frame. You have, let's see, I think some stuff's getting cut off here. Oh no, here. There's the element metadata. This also has to be a data frame. There's a metadata slot. This is just a list. There's a name slot. That's character or null. MSN set is another S4 class. This one comes from MSN base. So this class is from MSN base, designed more for proteomics experiments or mass spectrometry experiments specifically. So some of the slots here, you have an experiment data slot. That's an object of class MIAPE. That's minimum information about a proteomics experiment. Processing data is a slot that has to be MSN process. Assay data has to be assay data, annotation has to be a character, and so forth. So you can see these slots in an S4 class can themselves be other S4 classes themselves. You're not limited to things like integers or characters, although of course you have those sometimes. But these can also, you can require that the individual slots also be particular S4 classes. Delayed array is a package on bioconductor for working with large matrices with delayed operations. This one's the structure of this one is a little bit simpler, just has one slot called seed. And this one doesn't actually have any requirements for what that seed the class of this seed object at all. This is class any. This is one special term in S4 land that means this can be an object of any class whatsoever. It might make some additional checks on it to see if it's something that is matrix-like, but it doesn't have any specific requirements on exactly what class it is. The S4 vectors package on bioconductor has a data frame class. This is essentially an S4 version of the data frames that we already use in R, but a little bit more formalized. Here we have, for example, the list data. This is the actual row column data. It's just a list. You have the number of rows as an integer. You have the row names, which can be either a character vector or null, and so forth. So how can we create an S4 class? So creating an S4 class is a little bit more complicated than creating an S3 class. You don't really need to do anything specific to create an S3 class other than create an object of that class by setting its class attribute. But for an S4 class, we have to formally define that class using the function set class. So here we're going to define an S4 class for our animals. So when you use set class, the first argument is just going to be the name of the class that we want to create. I call it animal4 since it's an S4 version of our animal class. I'm going to say this animal4 class is virtual. Virtual is a kind of a special class that means that you can't actually make objects that are just an animal. We don't want users to be creating objects that are just a generic animal. We want them to create specific animals like cats or dogs or whatever. So we can't actually create an object that's just an animal. This is useful when you want to define a class that's just a generic interface, but you don't actually want people to create objects of that particular class. You want to use subclasses that will specialize this in some additional way. So here, just having an object that's a generic animal, that doesn't necessarily make sense. We want to have subclasses that are cats or dogs that are more specialized. We can specify the slots, what slots this class have. All it's going to have here is just a name of the pet, and that's going to be a character. And with S4 classes, we can also create a validity function, and what this does is this is a function that whenever you call a function called valid object, which is frequently called when creating new classes or changing S4 classes like this, this validity function will get called before returning a new object of this type, making sure that it's actually a valid version of this object. So you can do things like check here, say, we just want our pets to have a length1 character vector as its name. We don't want name to have a length greater than 1. So here we're just checking that the name slot is only length 1. So that's what we're doing to create this animal4 class. Now we're going to create subclasses for cat and dog. These ones are a little bit simpler. All we're going to say is cat4 is a class that inherits from animal4. Dog4 is a class that inherits from animal4 as well. Alright, so again, we want to create some constructors so that people can actually create objects of our cat4 and our dog4 classes. Set class on its own doesn't actually create or modify anything. It just defines that this class exists as a concept in R somewhere. But now we actually want to create constructors so people can actually create cat4 objects and dog4 objects. We can create new instances of an S4 class using this new function. It's typically considered rude to ask your users to call new on their own. You generally want to create a constructor so they don't have to do that. You don't want them getting their hands messy with the internals of your class. So we're going to be creating a cat4 constructor and a dog4 constructor. All these do is take the name of the pet and create a new instance of either cat4 or dog4, and the rest of this new function just takes the values we're going to set for the slots. So in this case, cat4 and dog4, they just have one slot called name that is supposed to be a character. We don't have to do any checking that it's actually a character because we define that the slot name has to be a character vector. We define in the validity function that it has to be of length 1. So if any of that is not true, all of that will automatically be checked when we create a new instance of it. So now we can create instances of Mittens and instances of Duke, and by default they'll just use the default S4 print method, which looks like this. Let's go ahead. I'm going to create those classes here. I'm going to clear my R workspace and start a new R session as well, since it's been working for a little while. Alright. Let's create the animal4 class, create cat4, create dog4. Constructors for cat4 and dog4. And now we have instances of cat4 and dog4 named mittens4 and duke4. So let's also test, say, I give this 1. Well, this will try to create a cat4 object with the name is just 1. We didn't coerce that to a character vector anywhere, so when it tries to create a new cat4 object, it'll say, well, the name slot has to be a character, so this is invalid. I got a numeric vector instead. We can also test, so suppose we want to say cat4 is named Cat Stevens, but as a length 2 vector, well, now our validity method will catch that and say the name has to be just length 1 character vector. Alright, so now we want to print something a little bit more elegant than this default print method when we just type one of these objects and hit enter. So for S4 objects, we actually define a show method rather than a print method. And the way we define S4 methods is through a call to the set method function. So in S4, show is kind of like the S4 version of print. Close enough. So what we wanted to do is define an S4 method for this generic show function. The way we can do that is through a call to set method. The first argument there is the name of the generic function we want to define, that's show. Then we give it the signature, so that's essentially a vector with the names of the classes that we want to, that this method will be called when show is called with those objects. So here, show, if we give show an animal4 object, it will go and call this method. This could be a vector if we are working with a function, a generic function like plot that has two parameters that we could possibly dispatch on. And the next argument is just the function that will actually be called. So here, it's just a simple function. The same function as before, function, object. All it does is it prints out that it's a object of whatever class it is, named whatever its name is. So I'll set the method for that. And now if I create and show a cat4 object or a dog4 object, it'll use our new show method. So now suppose we want to create a new S4 generic function. So we want to create an S4 version of our speak generic function. So for an S4 generic function, the way we do that is with the call to set generic. We just give it first the name of the generic function we want to create, and then a function that will actually be called. That should include standard generic at some point. And standard generic will also have the name of whatever our generic function is going to be. So we call set generic. We want to create a generic function called speak. That function, this generic function, is going to be a call to standard generic on this speak generic function. So I will find that here. So now if I look at speak, it is an S4 generic function. And now we can define S4 methods on it. We can also see the existing, Alright, so let's define an S4 method for speak. We again can just use set method to do that. So we're going to set a method for speak, for the signature cat4, and for the signature dog4. And then we just give it a function, the same ones we've been using before, where we just print meow for the cat, whoop for the dog. I'll set those methods. To see what existing S4 methods we've defined so far, we can use show methods to do that. First, let's test the ones that we just created. So I'm going to use speak on my cat. Oh wait, I don't actually have a cat yet. So I have a mittens 4 here somewhere. Mittens 4 is my cat, okay. And Duke 4 is my dog, yes, okay. So let's ask Mittens 4 to speak. Now we'll use our new show method. And speak on Duke, we'll use our new show method for S4 dog. So we can see what existing methods we have for any particular S4 generic by using show methods. So if I do show methods on speak, I'll see the different signatures that we have. So we have a speak method defined for cat 4 and a speak method defined for dog 4. And I also have a speak method defined for any. Remember, any is one of these special terms that means what if I call speak with any class and it doesn't match any of these other methods that we've defined so far, it'll use this speak function. Now, but I don't remember actually setting a speak method for any. Do you remember doing that at any point? So we didn't actually create that on our own. So what is the method for class any? Does anyone have any guesses or ideas where that might have come from? Some what? Noise? Weird noise. So I think you're on the right track, yeah. So earlier on, we had created an S3 generic function for speak. And now we've created an S4 generic function with the exact same name. So we can use select method to find out the particular function that's being called for any particular signature. So let's find out what the function is for speak with signature any. If we do that, we see, well, it's our S3 generic function. So what actually happens is, first we'll see if we have any matching S4 methods for our S4 speak generic function. If not, it'll go to the default, which in this case we'll end up calling our S3 generic speak function. And so that's how, if I restarted my R session here, so I don't know if I actually have that set up right now, but if I called speak on one of my S3 classes, that would still work. So oftentimes we'll have S3 classes and methods living alongside S4 classes and methods, and lots of times we'll have S3 generic functions and S4 generic functions that have the same name, and they kind of live together in this way. So here's that simple example. We're asking Mittens 4 to speak, Duke 4 to speak, and they use our new speak methods. Any general questions on how that works so far? Okay. So that ends our simple walkthrough of S4 and S3. So now I'd like to go ahead and revisit our MS example package, and we're going to take a look at what we have implemented here using S4 methods. Because this package is designed to kind of teach bioconductor conventions. So S4 was used throughout this particular package. And this is just a simple package designed for very basic processing of raw MS spectra. So I'm going to start by looking at a function that'll be kind of helpful for other things. This is a function called SimSpectra. I'm not actually going to walk through all of this because it's kind of complicated. I just copy and pasted this directly from my Cardinal package, actually, where you could find it with a different name. So in my package Cardinal, I have this as Simulate Spectrum. This is mostly the same code, copy-pasted. It was just a useful function to have in this package. So this is just a simple function called SimSpectra. All it does is it does some fancy stuff, and then it eventually returns a new mass spectrum. So what is mass spectrum? So one of the main things this little example package does is it defines an S4 class for representing a mass spectrum. I'm going to start a new R session, and rather than actually loading this package from scratch, I'm just going to work through each of these different classes that I've defined here and the methods for them. So I'm going to start with set class for mass spectrum here. So mass spectrum here, it inherits from the S4 class vector. Vector comes from the bioconductor S4 vectors package. And so, so a lot of packages in bioconductor depend on this S4 vectors package. And all this S4 vectors packages is it tries to define some kind of base S4 classes for very generic notions of vectors and data tables and so forth. So the summarized experiment class that we saw is actually also inherits from vector at some point. That's kind of weird because it's kind of this 2D matrix-like object, but S4 vectors implements a very general idea of what a vector is. So all this vector class is, it's just a virtual class. And essentially all it creates is the expectation that there's a length method defined for this class and a bracket method so that we can subset this class in some way. And the reason I'm inheriting from this S4 vectors vector class is, well, two reasons. Firstly, because it gets us a few things for free. So this vector class implements a few things so that I don't have to implement them later. Things like having a metadata function, being able to get the links of the elements, getting the names, things like that. Having access to metadata columns and stuff. So some additional useful bioconductor stuff I get for free by inheriting from this vector class. The other reason is because one of the principles I mentioned for creating a new R package is that you want to play friendly with whatever ecosystem you're going to be working in. So if I wanted to submit this package to bioconductor, I should try to reuse as many of the existing classes as I can. So mass spectrum, if you think of a mass spectrum, it's very easy to think about it as a kind of vector. So it makes sense to inherit from this S4 vectors vector generalization. So that's why I'm doing that. This mass spectrum has 4 slots. One of them is MZ. This will just contain all of the MZ values for the mass spectrum. That's going to be a numeric vector. The intensities in a slot called intensity, that's going to be also a numeric vector. A logical for whether or not this mass spectrum has been centroided, and an integer vector that is supposed to contain the indices of any peaks that were detected in this mass spectrum. So that's all that's going to be happening here. I just call that, and if I can find a way to silence my computer. All right, I hope that works. All right, so I've created a formal definition for this mass spectrum class. Now the next thing I want to do is I want to create some checks on what a valid mass spectrum looks like. Because mass spectrum is a representation of some kind of real biological data, so we would expect that we have a certain idea of what makes a valid mass spectrum. So previously I had an example where I set the validity as part of the set class, called the set class. You can actually do that separately through this set validity function, and in cases where the checks are a little bit more complicated, it can be convenient to kind of split off this validity check into a separate function, which is what I'm doing here. Yes?
So why is there a dot before valid?
Why is there a dot before valid here? That's a good question. So It is perfect. Firstly, it is perfectly valid, as we know, to use dots in variable names in R. This is clear from the heavy use of dots in base R in names like dot data, dot frame. There is a good reason not to use them in many cases because these dots are actually part of S3 method dispatch. We can see that base R ignores this a lot and has dots in a lot of its names anyway. It's usually good practice not to do so. But the reason I have dot here is for two reasons. Firstly, R kind of behaves a little bit like Unix when it comes to names. So if I name something here in my global environment, I'm going to create a variable called .x. Now if I try to list all of the variables in my global environment, well, there's nothing there. I'm going to create another variable called just x. Well, I see that. I don't see .x. So anything that starts with a dot, by default, it's hidden. And so it's just one simple kind of way to distinguish functions that I'm going to be using widely and I want to be available versus functions that are kind of, that should be hidden or are part of some sort of internals thing that we don't really need exposed. This isn't something that's going to be exported to the user anyway, so there's no real reason to do this. It's just a naming convention that I sometimes follow, although I sometimes break this myself. But that's one. But yeah, so as kind of a naming convention, I will tend to have, I will tend to name more important functions with an actual, without this dot in front of it. I shouldn't say important. Functions that I'm going to be using more often and other people could conceivably use. I will name without a dot in front of it. Anything that's kind of an internals function or is intended to be called by another function that I want people to actually use, I will have a dot in front of it. That means if they look inside the environment for my package, they won't see them unless they set this ls all names equals true. So there's no real reason behind it. It's just a naming convention I sometimes use. You don't have to do that, but there's no formal reason for it.
The other thing I was going to ask is there a way either S3 or S4 classes to set like public and private variables, or is that really
So the question is on public versus private variables in S4 and S3 classes. And the answer in both cases is technically no. With S3, people can do whatever they want with S3, and they will do whatever they want with S3. S3 doesn't really have any checks on it, so you shouldn't expect things to be private in S3 other than hoping people don't mess with it too much. With S4, nothing is actually stopping people from directly accessing the slots, but it is general good practice, and certain people like Bioconductor will typically require this for people who write code for packages and things like that. Will typically say that you should not access the slots directly of any S4 object. So typically you will want to define accessors to these slots that you want people to actually use and make available. Again, there's no way to actually enforce that I'm aware of. So if people want to access these slots directly, they can and they will. If they try to do that in the package they submit to Bioconductor, they'll probably be yelled at for it. But there's nothing actually stopping them from doing it besides that. But in general, that's the general protocol for the way you should define that. Is anything that's just a slot, you can kind of consider it to be a private variable, even though there's nothing actually enforcing that. And anything that you want to be public, you should create some sort of accessor function that people will actually use to access it. And we'll actually see some accessor functions that we've created for mass spectrum here. All right, so I'm creating a function called valid mass spectrum here. And all this function does is it takes what should be a mass spectrum object and it goes and makes sure that this is a valid mass spectrum object by doing some checks on it. And something that is, at least as far as I know, required by bioconductor, and I'm not sure if CRAN requires this, is that bioconductor asks that these validity functions actually return a full vector of all of the errors that were encountered. And it just, so this should return true if it is a true valid object. Otherwise, it should return a character vector of all of the things that are wrong with it. So to do that, I'm going to start off by just creating errors as null, and I'm going to be appending new strings to this as I go along if I find any errors. So the first thing is I'm just going to check if the MZ values are in increasing order. That seems reasonable enough. And if not, I'm going to add an error message that the MZ values should be sorted in increasing order. Next, I'm going to check that the length of the MZ values matches the length of the intensities. And if they're not, I'm going to say the length of the MZ values, and I'm going to say what that length actually is, must match the length of intensity. I'm going to say what that length actually is, so people can see which one is wrong. Here, I am checking the peaks slot. So the way that I'm thinking about this mass spectrum class is these peaks are just supposed to be the indices of locations of peaks in the mass spectrum. There are certainly other ways that you might treat this peak slot, but this is the way that I'm treating it. And so here I'm just going to check that any indices in peaks here are actually valid indices in terms of the number of data points in this mass spectrum. So if any of those indices are out of range, I'm going to say these indices are out of range. So if there are no errors, and errors is still null, this will return true. Otherwise, it will return a character vector with all of the problems with it. And I can set this as a validity for this mass spectrum by using setValidity and giving it that function. So let's do that. Okay, so now if I wanted to, I could create a new mass spectrum object with new. Let's see, intensities, let's just say 1 through 10. MZs, just 1 through 10. Intensity, just create some normal variables, or uniform variables. I need to specify centered, false, peaks. What am I doing now? Oh. Somehow, I actually left a bug in this code. So here I'm referring to the slots using object at the name of the slot. Somehow I had accidentally left just peaks here rather than object at peaks. And somehow that made it into the version that you got. So now you got a bug that you can correct. All right, let's try that again. So let's create a new mass spectrum. All right, and so that worked. And now we'll just print using the default S4 show method that just essentially prints all of the slots individually. Now let's try something that should give us an error. Say the MZ values are 1 through 5. The intensities are still length 10. Well, the length of the MZ values need to match the length of intensity. Okay. Set peaks equal to null. Peaks is supposed to be an integer, didn't get an integer. All right, so we can see that we're having some really basic checks done. Here, our validity method found that the length of our MZ values and intensities didn't match. Here we got an error because one of our slots was not of the expected class. So again, we shouldn't really ask our users to use this new function to create new objects. So let's create a constructor that will create mass spectra in a slightly more simplified way. So let's create a mass spectrum function. This just takes mz and intensity, and whether it's centroided or not, which will have a default argument of false. We'll check if the mz values are sorted. Because this is our constructor, we can do some additional things that are nice for the user. So we're going to sort the mz values for them. If they're not already sorted, then also rearrange the intensity so they're in the same order. We don't have to do that, but we'll be nice. And then we'll create a new mass spectrum with no peaks and return it. So let's use our new constructor. And that seems to work. Let's try something that should give us an error. And again, we need to make sure those lengths of those match. All right, so as we were talking about earlier, we should think of the slots in an S4 class as essentially being private. There's nothing to enforce that, but that's the way we should treat them. So anything that we want the user to actually be able to access, like say the mz values or the intensities or whether or not it's centroided, we need to create accessor methods so that the user can actually access those. And that's one reason we are depending on this package prot generics. So prot generics is a simple package. The only purpose of it is to give us some useful S4 generic functions that might be useful for proteomics and mass spectrometry. Alright, so prot generics just exists to give us generic functions that are useful for proteomics or mass spectrometry. So we have things like generic function for spectra, intensity, TIC, MZ, peptides, proteins, and so forth. All things that we might want to do with a mass spectrum object or any other object related to mass spectrometry. So this is one thing that is, again, part of being a good citizen of an ecosystem like Bioconductor, is reusing these same S4 generics, reusing the existing infrastructure whenever we can. So other packages like MSN-base and Cardinal also rely on these same S4 generic functions, so we don't get any weird collisions by different packages trying to define the same generics. So we just all rely on the same S4 generic functions. So what we're going to do now is we can just use some of these, like this existing MZ generic to create an accessor for the MZ values, for the intensity values, and so forth. So if I look at MZ here, it's a generic function. There's also a replacement function for it. We haven't really talked much about replacement functions, but we can also use these accessors or setters to replace the values. So we want to be able to let the user replace the existing MZ values with new ones. So we're going to first set a method for accessing the MZ values here, using set method, MZ value, or MZ, for the class mass spectrum, and it's just going to return the slot. So this is really simple, but it's important to do because of this kind of distinction between what should be considered private and what should be considered public. So we want people to use this kind of public API to access things like the MZ values and the intensities. And part of the reason for that is if we can assume that people are using these, we can potentially change the internal representation of our class, but code that other people have written, as long as they're using these accessor functions, should still work. even if we say decided to change the name of this lot MZ to mass or something, as long as MZ still returns the same thing, then everything should still work. So here, I just created a method for accessing MZ. We'll also create a replacement method. So this is the first time we're creating a replacement function. We do that with setReplace method, and the name of the function, or the generic function MZ here. This kind of replacement function takes two arguments, the object and the value. And we're just going to replace our MZ slot with whatever value the user gave us. And then we'll typically want to make sure that since we've updated the object, or we're returning a new object, we want to make sure that object is actually a valid mass spectrum object before returning it. So we're going to check that it's a valid object. Valid object just runs our validity method on it. So, going to, so here I have this little mass spectrum MS. Suppose I can access the MZ values, and if I want, I can replace them. And we can see that they've been updated now. Realize we haven't talked about replacement functions before, so are there any questions on that? Yes?
This is more general, I guess. Is there a reason for why is it on the arrow instead of
Well, there is an equal sign as well.
So, what I remember, so there are the equal sign and the arrow are almost always, but they're not quite always equivalent. So the equal sign means assignment unless it's inside the invocation of a function, in which case it specifies which argument we're using, right? Whereas the arrow, even in the invocation of a function, always means assign this to the first right? And there's something that I vaguely remember about there being a particular button on really old keyboards that did the arrow. So it didn't used to be two characters. A long, long time ago, from my understanding, which is one of the reasons that it's sort of a good idea. And then it was just, it's more evocative of what's happening. Like, taking this value, putting it over here, assigning this, right? But yeah, so that's long before my time. I've been on the keyboard, and whatever button that was. I don't know if it used to be one, but yeah, that's my understanding of the history. And then people just they kind of like it, and also there's this like subtle litigation of what usage.
Yeah, so there is this equals operator too, and probably in 99% of cases or something like that, it'll do the exact same thing that this arrow essentially is doing. The main difference being that the equal sign is used when you're specifying the parameters in a function. And you can even do it in a different direction, although I wouldn't. And there's also this one that uses the double less than symbols or double greater than symbols if you're doing it in that direction. That does something a little bit differently that I'm not going to talk about because you usually shouldn't do that either. But essentially what we need to know for here is that we can create a replacement function that we can use to replace our slots and update our object like so. And the rest of these are just some additional replacement function, or some additional accessor functions that I'm going to define. The only one that's kind of actually interesting here is the TIC one that It doesn't actually access a slot, it just sums up the intensities. Length, I need to decide what I'm going to use as the length. MZ and intensity should be the same length. And here I'm going to satisfy the requirements that this vector virtual class that I inherited from requires of me. I need to have at least a length method and a bracket method for this mass spectrum to be a proper vector. And so I can define a method for the bracket operator, like so. For the bracket operator, I can takes up to, we'll take up to potentially 3 or 4 arguments. 3 arguments here, or 4 arguments, excuse me. So you have I, J, ... and drop. For if I'm using replacement, there would also be an additional value that I could potentially be assigning. Here, a mass spectrum, I'm just thinking about it in 1 dimension, so I'm just going to use I here. And for this, what I'm going to do is, when we get the length of the mass spectrum, I'm going to do something a little bit complicated, not super complicated, to update which peaks are being selected there. And then I'm just going to subset the MZ values and subset the intensities with whatever the user is subscripting there, to make sure that it's still a valid mass spectrum object after doing all of this, and then return it. So now, MS here, if I subset it, say, to 1 through 5, I can just index or subscript my mass spectra like I would any vector now. And lastly, but certainly not least, I want to define a show method so that I'm not just printing out this full default description every time. And so, what I'm printing out is I'm just printing out it's a mass spectrum. I'm going to print out the mass range, whether or not it's centroided, the number of data points in it, and the TIC. Alright, so that's the basics of our little mass spectrum object. You could certainly make it more complicated. MSN-based defines a spectrum class that is kind of similar but much more appropriate for real data. Any general questions on what we did to create this? Yes?
Vector objects that, in order to be functional, have to define these 2 methods. Does it only check that when you try to contain an object that inherits from a vector? It's like why the way things are evaluated and mass spectra are, it seems like in order if you try to set that class, and then you don't set that class.
I don't think that vector tries to actually verify that those exist or not. What that really means in the case of this vector class here for bioconductor is there are some additional methods that they define. Like, for example, since mass spectrum inherits from vector, I could use lapply or sapply on it, using the S4 vector's own definition of lapply and sapply for vector objects. So I'm able to use sapply or lapply on mass spectra for free, essentially, and that requires that I have implemented this length and subscripting method.
So throw an error.
Right. I don't think it does anything to actually check that I've defined those anywhere, since I don't think that it could do that. It just means that vector at some point has some methods that rely on you having defined these somewhere. Any other questions? Okay, so let's now take a look at some other simple methods that we have defined for mass spectrum here. So one thing that we might reasonably want to do with a mass spectrum is just to plot it. So here we're going to create a plot method for our mass spectrum. Remember, plot has two arguments that it could dispatch on. So we're not going to really care about we actually are going to, I forgot I had two of these. So we're actually going to take advantage of that and do something slightly different depending on whether we give plot just one mass spectrum or if we give it two mass spectrum. So we're actually going to define two plot methods that dispatch on both x and y. The first one here assumes that we're just getting a mass spectrum object and that y is missing. So missing here is another one of those kind of special values like any that just specifies why was not specified. So here, all I'm doing here is I'm just going to I'm going to have an add argument that allows users to overlay this on top of another plot. If they're not adding it, I'm going to create a blank plot with the appropriate MZ limits and intensity limits. Then I'm going to draw the spectrum, and then if there's any peaks, I'm going to additionally draw and annotate those peaks. So let's go ahead and just take a look at that first. So I have a very simple mass spectrum here that I just created from a random uniform variable and a sequence 11 through 20. And the plot method seems reasonable. I'm going to go ahead and take advantage of my sim spectra function. I need to actually define now to create something that looks a little bit more realistic. So let's plot this spectrum S. So that looks a little bit more reasonable, a little bit more like an actual mass spectrum, I think. So we just have the MZ axis here, the intensities here. I've set up the default arguments of plot here so that they're nicely italicized MZ or intensity. I do something a little bit special if there's some peaks, but we haven't added any way to actually find those peaks yet. Now let's do something a little bit different if the user passes two mass spectra. So to do that, all we're doing is we're still setting a method for plot, but instead of mass spectrum and missing, the signature will be mass spectrum and mass spectrum. So you could conceivably have lots of plot methods that are very particular about what arguments you give to them and do something very specific if you want to. And all I'm going to do here is I'm going to plot both of the mass spectra, but one in the negative direction like this. So you can conceive that this might be useful for comparing different mass spectrum in some way. How's everyone doing? All right. Okay, so let's do something slightly more complicated. Let's implement some kind of signal processing for this mass spectra. Actually, let me simulate a spectrum that is deserving of a little bit of processing. So there's a little bit of a noisier mass spectrum, maybe a little bit too noisy. Okay, let's work with this. All right, so let's create some methods for some sort of spectral processing so that we can say remove some of the noise from this, reduce the baseline, and eventually try to do some kind of simple peak picking. So first, I'm just going to create. So lots of times when you have an S4 class like mass spectrum, it's a good idea to, when you create methods like smooth noise or fine peaks or things like that, that you might conceivably want to reuse for different kinds of objects. So say I could conceivably want to both smooth noise on a single mass spectrum or smooth noise on a class that represents a collection of mass spectra. That seems reasonable, right? So anytime you find you might want to reuse the same function multiple times, that's a good time to actually go ahead and define some sort of generic function for what you want to do. So here in this package, I have one R file dedicated to creating all of the S4 generic functions that I want to use. So I just have this all generics.r file, and this just defines generics for smooth noise, remove baseline, find peaks, bin peaks, and so forth. And if you eventually look at MSN base or Cardinal, I've kind of neatly chosen these exact names so they don't conflict too much with those. If you're actually implementing some sort of spectral smoothing or processing workflow like this, you should probably depend on MSN base so you can use the existing generics for these that come there. So for example, I'm going to load MSN base here. And I can see that MSN base has its own generics defined for things like pick peaks. Let's see, what are some other ones? Yeah, so MSN base already has generics defined for things like pick peaks, normalize, remove peaks, and some other things like that. Cardinal for mass spec imaging has its own versions of some generics like this. So the main thing I want to emphasize here is whenever you're doing something that probably has some sort of existing infrastructure in bioconductor or whatever ecosystem you're working with, it's always a good idea to reuse what is already there as much as you can. I'm kind of breaking that rule here just for the simplicity, so this little example package doesn't have to rely on those packages. That's not necessary in this case, but it's usually a good idea to do that if you can. So here I'm just defining the methods for all of these generic functions that I have, and I'm going to start off with smooth noise here. So smooth noise, I just want to smooth the spectrum a little bit. So I'm going to create a method called smooth noise that works on a mass spectrum, and it takes an argument half window that defines how the smoothing radius essentially. And because I'm thinking ahead, and conceivably I can think of a time where I might want to reuse a function that applies a Gaussian filter to something, or I could also conceivably want to improve smooth noise, this smooth noise method later to do different things and have an option to use either a Gaussian filter or a Savitsky-Golay filter or these other different kinds of things. I'm going to try to break up my methods and functions into small kind of bite-sized pieces so they're easily reusable in that way. So here smooth noise is going to call this Gaussian filter function. And all this Gaussian filter function is going to do is it's just going to create a little Gaussian kernel using R's denorm function. And then it's going to use R's convol function to just apply that Gaussian filter to the intensities. I'm going to update the intensities in my mass spectrum with that smooth intensities. And it's always a good idea whenever I'm working with some sort of S4 class that's updating the object and returning a new object to make sure that it's still a valid object of that kind, and whatever functions I used there didn't mess with it in a way such that it's no longer a valid mass spectrum. Is that a question, or?
Sorry.
All right, so let's create this smooth noise. I'm going to go ahead this mass spectrum that I have here. And now I'm going to plot these two. So the top one here is the original spectrum, and the bottom one here is the smooth one. Looks a little bit smoother. Let me try a wider window. Now it's quite a bit smoother. I'm not sure how smooth we want it. Pretty smooth, but still preserving a lot of things. So again, this is just a few basic functions, not really intended for actual use, but to show what we can do. So let's now create a simple function for removing the baseline. So here what this one is doing, again, I'm going to think ahead and say, well, at some point I might want to use a function that all it does is estimate a baseline. So I'm going to create that as a separate little function here. And here we get into something that is here I'm actually going to be calling a function called loc_max that we're going to be talking a little bit more about tomorrow. Because to remove the baseline, the way that I'm going to decide we're going to do that, at least in this little package, is what we're going to do is we're just going to find all of the local minima in the spectra, and then just interpolate all of those local minima together to estimate the baseline. Now to do that, I need some sort of function that actually calculates the local maxima within some sort of sliding window, or somehow finds the local maxima or the local minima in some sort of vector. And we're going to talk a little bit more tomorrow about some different iterations and versions of this function. But for right now, I'm just going to leave that as is and say that this is loc_max finds the local maxima of some vector. So here for my estimate baseline function, I want to find the local minima. So I'm just going to find the local maxima of the negative intensities. Then I'm going to make sure I have reasonable values at the beginning and at the very end of the spectrum, and just interpolate the baseline with R's across function. So I will try that on the smoothed spectrum. Oh, I need to these. Now we plot this version. So here is the version with the baseline removed. So here's the smooth version, the original version, after doing some smoothing, maybe a little bit over smoothing, I'm not sure, and doing some baseline removal. And the next thing I want to do will probably be the last thing I do just as part of this demonstration, will be to create a little function that finds the peaks. So here let's create a method for finding peaks. This will just call another function called findPeaks that also uses the local maxima to find the local maxima. It uses a really simple method for estimating the noise. It's just going to fit a very, very smooth curve to this, so smooth that it's going to basically ignore the peaks. This is just a function from our stats package called Friedman Super Smoother. It just fits an extremely smooth curve. It's a very simple way of estimating the noise that should probably be more complicated than that, but it'll work well enough for this demonstration. So it'll estimate the noise with that, get the local maxima, find out first which intensities divided by the noise are greater than whatever signal to noise ratio we've decided on. Both of these will be returning indices into the mass spectrum vector, and we're just going to get the intersection of these indices. define which are both local maxima and also greater than the signal to noise ratio. All right. S4, find peaks, S3. I'm not sure why this is plotting everything so small. Well, now that we're trying to plot it, our plot function finally has something to do when it has actual peaks information. We can see what actually changed in our most recent iteration of this mass spectrum object. So this str function is just a quick way of looking at the structure of essentially any R object. There are lots of times that it's useful. It basically just lists whatever slots you have. If it's some sort of list-like object, all of the elements of the list, and then a very compact summary of what those slots or list elements or whatever have you actually are. So this just tells us each of these are formal classes called mass spectrum. They have these particular slots, and these are the values there. So here, in all of these, we've done some sort of smoothing, baseline reduction, and so forth. So mostly just the intensities have been changing, and then here, for find peaks, we assigned an integer vector to peaks, giving the indices of those peaks. So now we have peaks here is an integer vector, giving the indices of whatever peaks we actually detected. We can see here that maybe the noise was estimated kind of too high in some regions. Okay, so far we've implemented a mass spectrum class. We've implemented a way to plot this class, and we've implemented some basic methods for a very, very basic processing workflow that smooths noise, removes baseline, tries to detect peaks, and so forth. The last thing I want to look at is, it would be nice if we had some sort of object that can hold a list of mass spectra that is aware that they are all mass spectrum objects. So here I'm just going to create another class called mass spectra list, so that if we have a list of a bunch of mass spectra, we can do something that is aware that those are mass spectra and not just an ordinary list. So here I'm going to create a new class called mass spectra list. This inherits from simple list. This is another class from S4 vectors. And again, inheriting from simple list means we get a number of things for free. It means that our mass spectra list will behave basically like any ordinary, like a simple list specifically, which itself behaves mostly like an ordinary R list. But in particular, simple list has a slot called element type, which lets us define what all of the elements of this list, what type they should be. And this is something that simple list already implements on its own. By default, a simple list will have element type equal to any. So ordinarily, one of these simple list objects doesn't impose any constraints on what kind of object the elements actually are. We're going to, rather than create an actual constructor for this mass spectra list class, we're actually just going to create a coercion method where if you have an ordinary list of mass spectra objects, you can coerce it to this mass spectra list object using as. I figure probably if someone has a list of mass spectra objects, they're probably starting in some kind of list, so I'm just going to implement a way to coerce them into a mass spectra list. So firstly, what's going to happen here, the way that we create a coercion method that we can call something like this. So if I had a list called spectra, I would be able to call this coercion method like this, as spectra, mass spectra list. And this is generally the way that we coerce S4 objects back and forth with each other rather than creating brand new, rather than creating a bunch of brand new functions like as.massSpectra list like you see in base R with like as.matrix, as.data, .frame, and so forth. So in S4 land, we try to do things using, at least when we want to coerce something, using this as function, or this as generic function, which then has methods. So here, I'm just going to coerce to simple list. We're going to use that to create a new mass spectra list. One thing about this new function that we haven't talked about yet is if we give this new function an object from one of its parent classes, it will essentially use that as the base object and create a new object by just updating whatever other slots we give it. So here, we're coercing to a mass spectra list. So to a simple list. So here 2 is a simple list. A mass spectra list is also a simple list. So new here, we essentially use 2 as a prototype to create a new object, where the only thing it changes is it sets the element type equal to mass spectrum. So that will say all of the elements of this mass spectra list need to be a mass spectrum object. Then we'll check that it's a valid object, which will, for a simple list, to verify that all of these are mass spectrum objects and return it to the user. So one of the places that this is used is in this sim_spectra function. The first argument here is just an integer specifying the number of spectra that you want to simulate. And if you simulate more than one spectrum at once, it'll essentially give you a list of mass spectra that are then coerced to this mass spectra list. So here, at this point I'm going to go ahead and just load the package itself so we can see here. So I'm going to simulate, say, 1,000 mass spectra. So now S is a mass spectra list of length 1,000 that contains 1,000 mass spectrum objects. And so now if we wanted to, we could define methods on this mass spectra list. So we could, for example, create a new smooth noise method that operates on a mass spectra list that just applies this smooth noise method to all of the mass spectrum objects in this list. And so that is essentially what I'm going to ask you to do kind of for homework. So here we looked at this simple MS example package. I'm going to ask you if you haven't already, and I guess I'm not actually going to check that you've done any of this, but if you want to, fork the package to your own GitHub repository and then git clone it to your own computer so you're working with your own version of this MS example package. We did all of this. We took some time to explore the existing S4 classes and methods in this MS example package. The main two classes that it implements is mass spectrum, which just stores a single mass spectrum, mass spectral list, which stores a list of mass spectra. So now my question to you is, what are some other useful methods or classes that we could write to extend this very basic package? Does anyone have any obvious ideas? Well, just a couple ideas. The first one I already described to you, but as a homework assignment, you could write processing methods. So you could write new methods for smooth noise, remove baseline, and find peaks that operate on a mass spectral list. All they would need to do is just apply the method smooth noise, remove baseline, or whatever to each of the mass spectrum in the list. That's not too hard. Another thing you could do is create a mass peaks list class. We didn't look too much at the peak picking functionality or the bin peaks method, but suppose we want to have, so a mass spectral list just contains mass spectra, but suppose we want to have a specific kind of list for containing mass spectra that have been peak picked and have indices for where the peaks were located or were detected. We could create a mass peaks list class that requires all of the mass spectrum objects to have been peak picked or centroided or something like that. So some things to think about is, what should a valid mass peaks list object look like? What methods could you define for it? What methods should we define for mass peaks list versus a mass spectral list? That's something that you could kind of decide and do something specific for spectra that have been peak picked in some way, or that are just peaks, versus spectra that may be profile mode instead of being centroided, or which have not had any peaks detected at all. Another thing you could consider doing is write your own coercion method for ads, for coercing either a mass spectral list or one of these mass peak list potential classes to another kind of class like summarized experiment, although we mostly talked about summarized experiment in the context of genomics. There's nothing actually that requires it to represent a genomics experiment. By default, all it has is just some sort of list of assays, which could very easily be a list of mass spectra that have been processed and aligned in some way, along with row data and call data for the MZ values and the samples and whatever. So I want you to try at least a little bit of this. The first one here shouldn't be that difficult. The rest might require a little bit of thinking about, not because they're necessarily hard, but because there's lots of different ways you could approach those. But just think about, try some of this, think about what some other useful methods might be that you might want to implement, and that about wraps it up for our session right now. So refreshments will be served again, and at 3:30 we will come back for a keynote by Barrett Schlarke from our studio.